All right. So the last paper is titled Accelerating SAT-Based Planning with Incremental SAT Solving. It's going to be presented by Stephan Gocht.
Yeah, thank you for the introduction. Hello to everyone. My name is Stephan Gocht, and I'm going to explain to you how we can use incremental SAT solving for SAT-based planning. And what you're going to see will be kind of similar to a bidirectional search, but also very different because it's SAT-based, but we will see. So let's start. What kind of planning are we considering? We are just considering classic planning, which means we want to have a finite state space. We want to find actions from an initial state to a goal state. The actions are deterministic, they're not non-deterministic, and we are also not considering any cost or anything, so really very basic planning. So let me give you a short repetition of SAT solving and the terms I will use here so you know what I'm talking about. The first, we are only using Boolean variables which are either true or false, and we will use them pure or in its negated form. And if we want either, then we just say it's a literal, and then we can use disjunction of literals, so or of multiple literals to get a clause. And the formula is simply the conjunction and of multiple clauses. And then we have basically a CNF formula like this one here. And what a SAT solver does is to check if such a formula is satisfiable or not. So this means it tries to find assignments to the variables such that the formula is true. And the problem of satisfiability is, of course, to determine whether such a solution exists or not. So how can we apply this to planning? So the general idea is that we will construct a formula fi that encodes that there is a plan of length I. So we start with a formula that encodes whether there is a plan of length 1. We give it to the SAT solver, and the SAT solver says us, no, there is no such plan. And then we create a new formula f2, asking if there is a plan of length 2, and give it to the SAT solver, and so on. So of course the question you might ask here is how do we transform like a PDDL style problem into SAT solving? There are different approaches to do this, and actually we don't really care which approach is used, so we can use all of them. And what we'll make a more abstract view, so we'll just say, okay, we have some initial clauses that describe us the initial state. So this could be a concrete state where like is only every clause is only one literal, but could also be a more complex initial state. We don't really care. We just say, okay, there are clauses describing the initial state. The same for the goal state. And then we have transition clauses that describe how we can manipulate the state, like with actions. And then we have this kind of clauses, and we can use this to construct the formula. Like this is a general formula, but I'll have more easier to understand example later on, so don't care too much about it. Just we have these three kinds of clauses. And yeah, what we're going overall to do is like we take the PDDL style planning problem, and then we use any SAT-based encoder like Madagascar or Freelunch, or we can use any other encoder that just cannot transform the problem in terms of these three kinds of clauses. Then we will use our tool IncPlan, and this will call a SAT solver multiple times. And we are using a SAT solver supporting the IPASIR interface. This is an interface from the SAT competition. And this allows us to use basically every incremental SAT solver that also competes in the SAT competition. So what we did is we took every SAT solver from last year's SAT competition, tried them out, and like this year we can use the SAT solvers from this year's competition, plug them in, and run our tool. And it's very nice because we have the standardized interface. Okay, so what is this incremental SAT solving I'm talking about? The general idea of SAT solving is, of course, you give a formula to the solver, he solves it, and you get an answer. But then the solver basically gets destroyed, you take a new solver for the next formula and standard SAT solving. But this might not be clever. Because SAT solver learns a lot of things about the formula he's solving, like he's learning new clauses, he's gathering heuristical values about how important variables are, how important clauses are. He can also gather like good partial assignments of part of the formula, And if you use normal SAT solver and solve it and then use the same formula again, he's forgotten everything. So the idea with incremental SAT solving is that we will use the same instance of SAT solver and just add new clauses on top of the old ones after we solved one instance. So we basically have two methods. We can add clauses and then we can solve. And then in the solve we can also set some assumptions. These are like temporary unit literals which are only for this concrete solve step. And then afterwards, after you have solved it, these assumptions are removed. You can add new clauses and you can solve it again with new assumptions. And this allows you to reuse all the things I've said, and you also don't have like this input overhead, because if you're adding similar parts of the formula over and over again, the solver has to parse it and so on. So you save this as well. This is the very idea of incremental SAT solving, to save this. Okay, so then how does this look for planning? Let's first look at the left side, where we do incremental and non-incremental planning with SAT solving. There we have like a time point. Time point is basically just a set of Boolean variables that encode one state. And what we say here, okay, we apply the initial clauses to this time point, and we apply the goal clauses, so we are checking if there is a plan of length 0. And if the solver says, okay, this is answered, then basically we throw everything away and construct a new formula with one transition, asking the question whether there is a plan of length 1. And again, the goal is only, goal clauses are only added to the last state, of course, because there we want the goal to hold. Then again, we remove everything and start over again. And you see this is like not too clever, because like the lower part of the formula always stays the same. So what we do with incremental SAT solving, the start is the same. We check if the goal state is already reached with the initial state. Then we only remove the goal clauses, add a new transition with a new goal clause, and then again only remove the goal clause. So everything the solver has learned about this part of the formula can be remained and can be reused for the next solve step. And then we basically go this step on and on until we find the formula with a solution. And from the assignment, then we can reconstruct a plan. So this kind of search could be understood as kind of forward search, right? We are starting with the initial state, and going from there on, we are adding new transitions. And so what you could do also is do the other way around. Like we could fix the goal state and add transitions from there, and could be understood as a kind of backward search. The question is, what is better, forward search or backward search? I mean, we can do both as well. We can do some kind of bidirectional search in SAT solving with incremental SAT solvers as well. And how does this look like? So the idea is that we have these initial clauses which are always applied, and we have the goal clauses which are also always applied. They will never be removed. Instead, we have new clauses that link two time points together in the way that they just basically say, okay, every variable in the one time point has the same value as the variable in the right time point. So these two states are identical. So this is now again checking if the initial state has already reached the goal state. Now what we do is just to remove this link and add new transitions to the left side and a new transition to the right side. So we can like grow both sides after each other, and then add a new link that again says the top two states are the same. And what we now have is like asking whether there is a plan of length 2, right? So one transition and second transition. And after we're done, solver tells us no, there is no plan of this length. We can again remove just the link clause, and everything the solver has learned, like on the left part and the right part, based on the goal clauses or on the initial clauses, can be remained. And then again, we can just repeat this process. Here in this example, I only added 2 transitions. You can, of course, also add only one, like one to the left, and the next step one to the right, and so on. So for evaluation, as I said, we took solvers from the SAT competition from 2016. And of course, we choose the solver who performed best for us. And we used the benchmarks from the IPC 2014 competition and from the AGL track, because this was a track where Madagascar, another very good SAT-based planner placed second and third with 2 variants. And we use the same limits, so 300 seconds time limit, 8 GB of RAM. Of course, we have another CPU, but I don't think it's too important. And so let's first compare like the non-incremental version with the incremental version. These plots are on log scale, and on the bottom side you always have the non-incremental version, on the left side the incremental version, and you can see for the single-ended incremental version, like where you just transform this idea to incremental SAT solving, we get in most cases a better performance. And we can also see we have tried different encodings, and like this effect shows on all of them. So all encodings profit from this incremental encoding. And if you now do the double-ended incremental encoding, or this bidirectional thing, then the speed up is even larger for a lot of instances, especially where we haven't seen a speed up before. Okay, then of course it's interesting, how do we perform comparison to Madagascar? And what is interesting here is that even the non-incremental version seems to be much faster on the cactus plot. And with the double-ended incremental version, we can overall solve more instances. But if we see on the right side, again, a log plot comparing on a problem base, it's both the existential encoding, like we use the same encoding Madagascar uses. We can see that these two approaches are really complementary. Okay, so as take-home message, the incremental SAT solving is definitely very beneficial, and whenever you can, you should use it. Another thing, it's really important to keep track of SAT solver development. Like Madagascar did a lot of planning-specific improvements to its own SAT solver, but still off-the-shelf SAT solvers are getting better every year, so we should keep track of this as well. And a future view is to use advanced scheduling techniques. For our approach, we really added, we tested for the formula for F1, F2, and so on. You can do more like jumping in exponential size or something. You can use planning-specific heuristics for a SAT solver. And we're also interested in what is really giving us the speed up, like is it the learned clauses or maybe other aspects of the solver. So thank you for your attention.
Questions? Yes.
So both in planning a SAT and bound model checking, people have previously worked on reusing learned clauses across those efficient iterations. Can you comment on, I mean, it seems like it's basically this in a more effective form?
Yeah, right. I mean, like the single-ended encoding is just basically the same. It has already been done. We have just like reformulated a bit and made it easy to use, like with different encodings. This is by using this abstraction. I mean, this abstraction is also already present in the encodings from the solvers. What is really new is the double-ended encoding, I think, where you can go from both sides. And I mean, there are also completely different approaches in model checking as well that use incremental SAT solving.
Like the incremental SAT solving looks to me like a more direct version of just saying we can keep those clauses that depended only on the assumptions being made in the previous call.
Right.
So is that the main thing that's going on here, like the keeping those learned clauses, or
yes.
are there other things that the SAT solver benefits from?
Yeah, I mean, this is what I say here is future work, right? We don't really know. Like it works, we get a speed up, we don't really know where it's from. From preliminaries I know it's not only the learned clauses, but it's more.
Okay.
Yes.
So is the def, the bound that you used, part of the assumptions?
Sorry?
So whenever you say that there are assumptions in order to know which clauses you can reuse,
right.
Is the def like the bound that you used last time?
I mean, we don't have a bound we use.
I know, okay.
The assumptions are really, I mean, like, for example, in here, we know that we will remove this clause, so we need to do some magic to be able to remove it, and we use assumptions to remove this clause, basically. I haven't gone into this because I didn't have enough time. But basically, yeah, we only need assumptions to remove clauses, so other thing stays always in the formula.
Yes.
Have you looked at the comparison to property-directed reachability?
No, I haven't. Sorry. I have to do this right, yeah.
So, yeah, I have one question. So I need to understand this I need to understand this more. So you're saying every clause that is learned, right, during search, is entailed by the knowledge base, right?
Right.
That's a property. So you're saying that basically, that in this case, when you have this double-ended encoding, the clauses that are learned are not are entailed by everything without the linking constraint. Is that right?
Right.
So I was checking your paper. So I mean, that's amazing. I think. So do you have a proof for that? A proof of? Is that trivial?
I mean, it's kind of obvious if you have this. Like, let me go through it. Like, what you do is to remove a clause is to add another literal to it, and then you can, like, if I add this not A, and then I give the assumption A, then the solver has to satisfy C. If I don't give the assumption A, solver can satisfy this clause simply by setting not A to true. And it's I have a proof. It's not in the paper, but I have a proof that every learned clause that needs C does also contain the activation literal then. And so basically it's marked which clauses are dependent on the clause and which not.
So what happens when you do like the simplification, right? When you have like a SAT solver that with the pre-processing and you put the assumptions, right? And everything gets simplified.
You have to do different pre-processing when doing incremental SAT because like you have between these time points, you have like variables where it links together. And if you do simplification, you cannot remove these variables. So you have to perform some specific kind of preprocessing. We didn't do preprocessing at all.
Okay.
But it's possible.
Okay, thank you.
Yeah.